আচ্ছা, এখন কোথায় আছেন?
বাড়িতে কলকাতায়।
কলকাতায় কোথায় বাড়ি?
আমার হচ্ছে দেশপ্রিয় পার্কের কাছে,
ও আচ্ছা আচ্ছা,
সাউথ কলকাতা।
হ্যাঁ।
আমি আপনার লেকচার শুনবো বলে তো এসে বসেছি।
আপনি তো ওটাকে বলেন, আপনাকে লোকজনকে দেখিয়ে এই ম্যাথমেটিক্সে পাগলা। হ্যাঁ, হি ইজ ফ্যানাটিক অ্যাবাউট ম্যাথমেটিক্স। হ্যাঁ, আপনি তো আমাকে যোগ্যই মনে করেন না
কি আশ্চর্য!
লজিকে।
একেবারে মা, এটার কোনো মানে আছে নাকি?
হ্যাঁ
ম্যাথমেটিক্স দিয়ে তো লজিকটা বোঝা যাচ্ছে, ফলে ম্যাথমেটিক্সে আপনি যদি ফ্যানাটিক হন তাহলে লজিকেও ফ্যানাটিক,
হ্যাঁ,
কোনো ব্যাপার না।
ঠিক আছে, আপনি এসেছেন, খুব ভালো লেগেছে।
হ্যাঁ
হ্যাঁ,
হ্যাঁ, শুনবো।
what is the time now? 6:55. We still have time.
Yeah, we do have time.
তবে আপনাদেরকে একটা গল্প বলি। হ্যাঁ, গল্প না, আসল ঘটনা। হ্যাঁ, ওই
হ্যাঁ।
আমার ফ্ল্যাট আছে কালিকাপুর, তো আপনি বোধহয় চেনেন।
হ্যাঁ হ্যাঁ
কালিকাপুরের দিকে
হ্যাঁ
ফ্ল্যাট আছে, তো সেখানে গিয়েছিলাম, বুঝেছেন।
হ্যাঁ
ওই গাড়ি করে গেছি, কিছু কাজকর্ম করানো আছে।
হ্যাঁ
তারপর আমার ড্রাইভারের ওয়াইফ শুনেছে, হ্যাঁ,
হ্যাঁ।
যে আমাকে নিয়ে ওইখানে গেছে।
আচ্ছা।
তখন ওকে ওই যে ডাবল মার্ডার হয়েছে
হ্যাঁ
গড়িয়াহাটে,
হ্যাঁ, কাকুলিয়ায় কাকুলিয়ায়।
কাকুলিয়ায়, যেখানে কি
হ্যাঁ
একটা ড্রাইভার আর
হ্যাঁ
মালিককে
হ্যাঁ
মেরে
হ্যাঁ
দিয়েছে।
হ্যাঁ হ্যাঁ।
তুই বলেছে যে এই কি সর্বনাশ। হ্যাঁ হ্যাঁ, তুমি ওইখানে মানে মালিককে নিয়ে ওনার প্রপার্টিতে গেছো,
হ্যালো।
দেখছো না ওখানে তো ড্রাইভারকে খুন করে দিয়েছে। হ্যাঁ, তুমি মালিকের কাছাকাছি থাকবে না।
আচ্ছা।
হ্যাঁ, দূরে দূরে থাকবে। হ্যাঁ, বুঝেছেন। তো আমিও বুঝতে পারছি না কি করব।
কিন্তু এটা ইন্টারেস্টিং, একটা সিঙ্গল কেস থেকে এরকম জেনারেলাইজ করা যে যে
না,
কেউ
জেনারেলাইজ না, লোকে ভয় তো ঢুকবেই। ইউ
হ্যাঁ,
ক্যানট ব্লেম দ্য লেডি।
দ্যাটস রাইট, ঠিক।
You cannot blame the lady. The driver was also murdered.
ইয়েস।
So she is worried about her husband. Identical situation. And she says, no, 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 keep away. Even if you go, you remain away somewhere. Let the guy get murdered. That is not a problem.
তো
Oh, Amit is there.
Who?
Amit.
Ah, hi. You see, I am forcing my lectures.
Yeah, that joke is old now.
No, but this is a true fact. It is not an invited talk. I suggested. And how can you people say no to me? So I took advantage of that fact. So Fred.
And we never wanted to say no to you either. We never wanted to say no to you either.
Yeah, that you know.
Fred, I suggested that, okay, let me give a talk. And these people have, out of politeness said yes. And this is a topic which very few people, somehow there is a forcing phobia. So,
So I guess that we can start in 1 minute because like many people are already.
Okay, whenever you ask me to
Yeah, sure.
start, I will start.
Amit, shall I introduce or it's your turn? I forgot.
Can you please do it? I don't think he needs an introduction, but
Yeah, that is for sure. Yeah, that's for sure.
Well, many people, no, I do better not to lose time. That I agree.
Yeah.
So
some people from my model theory course are also here.
Yeah, lots of students are joining actually, they can see.
yeah. So let me wait a bit. Just 1 minute, let me give.
Yeah, sure.
Oh, this October 24 is the last. Yesterday I went through it. So last time it was compiled was on October 24. Okay, so very happy to see many old friends again. And 21 participants. Okay,
Yeah.
including me.
Including two of you. You have two windows.
Including two of me. So not bad. I mean,
yeah. No, I think many more will be joining because naturally people used to be late by 5 to 10 minutes.
Okay, then thanks for coming. I don't know how satisfactory this lecture will be because this is a huge topic and quite technical and but it's not that it cannot be learned. It can be learned. Now people just use left and right forcing. But the initial thing, the main part of Cohen's work himself, which justifies, gives the thing, is pretty technical. But those parts people can easily assume and go away and work with it. So, what happened?
It's fine, I think.
Huh?
It's not going?
No.
Then I use this instead.
This one?
Yeah.
Okay. So, Paul Cohen is the only Fields medalist in set theory. In fact, in foundations of mathematics, logic, and so on. So far, there is only one Fields medal awarded. That was awarded to Paul Cohen for an outstanding problem of what is written here as relative consistency of the negations of continuum hypothesis and axiom of choice. So the question also arises that how about relative consistency of continuum hypothesis and axiom of choice? That work was done by Cardinal. And during the course of my lecture, I will do that. So after Gödel's work, it was clear that you cannot disprove continuum hypothesis. Again, here this disprove is a slightly technical word because there is a notion of proof in first order theory. So in that sense, you cannot disprove. But how what can you prove it? And that one was also open. I think I don't remember very well the year, but it was before the war when Cardinal did his work in Princeton. I will be speaking on that. And finally, in '66, Cohen got Fields Medal. So between 62 and 66, he announced his work. So and this is a very, very landmark work in set theory. And I would say that today set theory is surviving a great deal because of the forcing. Okay, so already I have spoken that this requires, it's quite technical, it requires good knowledge of axiomatic set theory and logic. So I will give only overview and I will leave a lot of technicalities. Leave out a lot of technicalities. Okay. So first of all, since there are students also, what do I mean by this consistency? So I want to explain it by a very, very simple example. There are two words, by the way. It is not just consistency, it is relative consistency. So let us take the simple way, because people say, oh, whether this guy is consistent with this or not. And this is where the foundation of mathematics is hidden a bit. So let me give an example. So we all know that how group theory begins. I mean, you start with the definition of a group. So a group is a non-empty set G with a specified element E and a binary operation on G satisfying the following actions. I don't have to, this is associativity. This is multiply by E, this is called the group identity. Multiply by E, either way, you get, you don't change the value. And then every element X has an inverse. So this you are all familiar with. So this is how you begin. Here you should have no difficulty. And now consider the statement for all X, for all Y, X dot Y equal to Y dot X. Okay. So meaning of this is that this is the abelian property. If you can interchange, if you interchanging the order of multiplication does not change. So this is what is called commutativity. And what is its negation? So negation would be, negation would be, here it is saying that for all X, for all Y, X dot Y equal to Y dot X. And here it is saying there exists X, there exists Y, such that X dot Y is not equal to Y dot X. So this is precisely the negation. Now, if you prove A, I have put proved in a quotes, within quotes, then from the three axioms of group theory only. Then what will be proving is that all groups are abelian. So that is not the case. So you cannot prove this A from, so those who know some first order theory and proof in first order theory, I mean that part. So it would follow that all groups are abelian, and we know that there are groups which are not abelian. On the other hand, we also know that there is a group which is abelian. So you cannot disprove it also. So here what we have done is that we have given an example of we can give an example of a group, that means example of the model of what we have said, which is abelian. And therefore, this is what we say, that this is consistent with the three group axioms. And there are also groups which is non-abelian. Non-abelian means it will satisfy the negation of A. So we also see that the negation of that is also consistent with the three axioms of group theory. And this we say that A is independent of the three axioms of group theory, if both A and its negation are consistent with the three axioms of group theory. So this is an example of a theory, of a set of statements, namely the axioms of group theory. And there is another statement made with the language. And then we are saying that, we cannot settle, we cannot decide that statement A with the help of using the three axioms, or using whatever set of axioms you take. That is what is called independent. So you can just generalize it, it's a group theory, but you can see the general definition from here. So now I have to explain what is meant by relative also. So let me go to that. Now one should know that mathematical theory, there is nothing concrete. You write down your language and you write down your axioms. Those things are only concrete, and you start logically playing with them. So only thing that I would say is concrete is the axiomatization. YOLO. This one is not working. Why? So in case of set theory, the common axiomatization, I mean, this is what one works with. It's called the Germelo-Frankel set theory. And here, there is Jdf and there is Jdfc. So Jdfc is with choice. You also assume axiom of choice as an axiom, or here it is without choice. And I am, you all know it. So this is a first order theory with only one non-logical symbol, namely a binary relation symbol belongs to, and with a certain set of axioms. So we don't know, I mean, at the moment, it is not important what the Jdf axioms are. As I go along, I will keep on saying some axioms and their importance. What? Oh. So, now, point is that you have put a set of axioms, Jdf. The question is that, is this itself consistent? So whether using this, can you prove a statement as well as its negation? If you can prove, then obviously it is not consistent. That is what one means by consistency. So one question is that I have defined a theory. Is it consistent? And this is an extremely famous theorem of Gödel, that it cannot be proved in Jdf, that Jdf is inconsistent. So if it is not consistent, we say it is inconsistent, and we cannot prove that it is inconsistent. Not only that, we cannot also prove that it is consistent. So this is the second incompleteness theorem. And, oh, I'm sorry. Wait a second. So since Jdf is the foundation of mathematics, I mean, entire mathematics is done inside Jdf. The entire mathematics stands on the assumption that Jdf is consistent. And the relative, okay, I have to use this. So every consistency or independence result in mathematics are under the assumption that Jdf is consistent. And this is why we qualify them by adding relative to them. In other words, if you assume that Jdf is consistent, then Cohen showed that Jdf plus negation of continuum hypothesis, or Jdf plus negation of AC, that is also consistent. So that is under the assumption that Jdf is consistent. And as I said, entire mathematics is done on this assumption that Jdf is consistent. You are safe only in the sense that nobody will ever come up and show to you that Jdf is inconsistent. That is what Gödel has given us the. So what we do is that, so now I have explained, So now I have explained what does relative consistency mean, is that if Jdf is consistent, then Jdf plus negation of axiom of choice is consistent. That is what Cohen showed. What Gödel showed is that Jdf plus axiom of choice is consistent. again, what Gödel showed is that Jdf plus continuum hypothesis is consistent. And what Cohen showed is that Jdf plus negation continuum hypothesis is consistent. I will explain in detail what is the continuum hypothesis later as we go along. But there is a problem. You may think that if Jdf is not, you cannot prove Jdf is consistent. How do you go about it? So only way to go about it is proof theoretic. There is no other option. And this is also, a very clever way of doing set theory, where actually you are doing everything proof theoretically, but you feel as if you are working with the actual model, so to speak. So now, since Jdf is, you have assumed Jdf is consistent, the Gödel's completeness theorem says it has a model, but still it just take a bit of that this may not be a set. So whatever model at the moment it means, just think that your usual picture of model is what is applied here. So we fix a model. What the elements of V are, as usual, when you fix a group, just say let G be a group, what the elements, particular, any element, any group you fix, what the elements are, it does not matter. Only is that you have an interpretation of the belongs to as a binary relation, and whichever way you interpret does not matter. All that it, So all that matters is that V epsilon satisfies the Zermelo-Fraenkel axiom. So it is still, what is V? I have already confused you by saying that, the model also, in what sense it is model, those things. But for the time being, let us assume it like that. It will not hurt you. So the situation is almost the same as, so this part I have already said. So this part also I have said. So once we fix V, now people always ask what is a set. Okay. Now once you have fixed V, sets are precisely those which belongs to this universe. Okay. So by a set one means that an element of V, and everything is set. So functions. So usually the set theoretic way of defining function is define a graph. The graphs are functions. So that graph is also a set which belongs to V, and so on. So you are not, everything belongs to V is what is the restriction now, because you are working with that. Okay. So now I am going to give you that, while explaining the technique and such, or applying the technique, I have to give some example and work that technique on it. I am not going to take such a difficult proof as such a difficult result as continuum hypothesis or axiom of choice. That would be too hard to continue to illustrate with. So I have taken this statement. Take any set Y. So Y is any element of V, and whatever it is, finite, infinite, countable. Countable includes finite, by the way. Uncountable, whatever. It is consistent to assume that Y is countable. In other words, I will be able to give another model of set theory in which Y will become countable. And by countable, at the moment you can say that there is a function from the set of natural numbers onto Y. The thing is that if there is a model of set theory, then the collection, there is a, in that there is a collection of natural numbers, which actually due to something called absoluteness, which I will explain to you later, there is a map from natural numbers onto Y. In other words, I will build a model of set theory, and in that model, there will be a function which will contain Y, of course, and in that model, I will find a function from set of natural number onto Y. This, in my opinion, is the simplest. I have always illustrated with this because this is the simplest example where I can use forcing technique, and still the result is quite shocking in some way. So this means that if Jdf is consistent, then the above statement is consistent with the axioms of Jdf, which just now I have explained you that starting with a model of a ground model, V, I can get hold of another model in which Y belongs, and in which there is a function. So that means graph of the function is inside that model, whose domain is a set of natural numbers and whose range is precisely Y. Okay. Now comes, I had told you that, fix a model V. But what does it mean now? At the moment, usually you say there exists a set and so on and so forth, but you are working you are looking for the model of set theory itself. So what do you mean by that? So there is a notion called class. Let me go ahead a bit and then come here. So, so by a class, we actually essentially mean a formula of the language of set theory with a free variable x, and there may be some other sets needed to define, may have been also used. They are called parameters. So by a class, there is hardly any difference between the notion of a class. By the way, these students should listen very carefully, because many students, whether they are doing logic or not, they always ask. Let me see, there is something in the chat. This is. Okay. So many students from every branch of mathematics, as soon as they ask what is a class, particularly if you begin with algebraic topology or things like that, you say, oh, a category consists of a class of sets, and then people immediately ask what is a class. So this is the definition of class I am giving. It's very important even from mathematics, for mathematics experience. So there is a formula, and what is a formula I will tell you later. There is a formula. So this is expressible formally in the language of set theory with a free variable x, and it may be using some more sets as a parameter. And then there is no difference between formula and the class. But how do you think of? Usually you think of class as a collection of sets. So you think of those sets X for which the formula phi X is a theorem of Jdf. It's provable. Formula phi is provable using the axioms of Z. That means it is a theorem of set theory. Again, provable here means it is a theorem in the sense of first order theory. So that is what a class is. A class and a formula can be identified together, synonyms. They can always think of it as a synonym. But Actually, when you are working syntactically with this formula. Everything is going on proof theoretically. But when you are trying to think of as a collection, you think of those objects, those sets for which phi x is a theorem of Jdf. Another way of thinking of class is it is a collection of sets such that membership to that class can be expressed by a formal language, by a formula in the formal language of set theory. So membership there, for example, if you say ordinal numbers or cardinal numbers, so whatever you say, the definition can be expressed in terms of a formula. It can be formally expressible in the language of set theory. That is the class. Now, you can almost treat classes like sets. So suppose M is a class defined by the formula phi x. That means this is the collection of all sets x, need not be a set in itself, for which phi x is a theorem. Similarly, suppose N is a class which is defined by psi x. Then phi or psi is also a formula. Okay? And then if you look at what are the sets x which satisfies phi or psi. So obviously you mean that, so you mean that that x either belongs to M or belongs to N. So if M and N are class, so is M union N. For the complement, that means those sets which does not belong to M, you use the formula negation phi. Okay, and we have assumed the consistency of B kind of thing. So negation phi holds, X satisfies negation phi if and only if X does not satisfy phi. And therefore you get precisely M complement. Similarly, phi and psi will give you M meet N. So you can see that you are able to treat M and N just like as if they are sets, but in effect, you should be always aware that they are not sets, and we are only playing with the formula which defines the thing. This is very, very important. And also it is very heartening that you can treat them like sets. Okay. Now what does it say? This formula says if any set x satisfies phi x, then it should satisfy psi x. So this just says that M, every set that belongs to M also belongs to N. Therefore, instead of what you call subset, in the case of class, you say subclass. Okay, so all the notions of set theory, usual notion of set theory, union, intersection, complement, subset, so on, they are available to you, and you can treat them like sets. There is also axiomatization of set theory called Gödel-Bernays set theory, where the class is a part of the axiomatic system. Okay. Now, if I write X belongs to M, okay, the usual meaning we will keep in mind that X is a member of M. And actually what you know, what it means is that phi X is provable in Jdf. So this is what is class R. And my next slide will show you that take a set Y. And then consider the formula X belongs to Y. Okay, this is one of the formula of set theory. Now this is a formula where of course X is free, is a variable, and Y is this set that you have started with. So this is an example of a formula with parameters Y. That is what I had meant when I was talking of that your phi X will be a formula with parameters. It may be using certain sets also. To define the collection M, you may be using certain sets also to describe that, membership to that. And now what are the X which satisfy X belongs to Y? Okay. And there is a subset axiom which says that if Y is a set and phi is a formula, then the set of all X such that it satisfies X in Y, which satisfies the formula phi X, is a set. So that is what is called subset axiom or comprehension axiom. So here is the first example of a axiom of Jdf. So it will follow from the axioms of Jdf that the intersection of a class is a set and a set is a set itself. And not all class will be sets, that has to be shown. So I'm about to show it, but if you have a class which you can show that it is not a set, then we call it a proper class. Okay. So if I only say class, I will mean either a class, proper class, or a set. But if I say proper class, I'm making it a point that that class is not a set. Now, let us see. You have seen this argument very often. So, does there exist a proper class? And one of the most famous axioms, where one of the most famous what is called paradox, was invented, was presented by Bertrand Russell, and who showed that if you go by the naive description of what Cantor has given or naive definition of set that Cantor has given, then there is a problem. Namely, he said that the collection of all sets itself is not a set. And see what it is saying. So I'm saying that this is a theorem. Okay. So there does not exist a set Y which contains all sets X. Okay. So this I am going to prove using the axioms of set theory. And therefore, you have first example of a proper class. I'm sorry for the experts. I'm really, my main goal is to address the students. Okay, so let us see that no, suppose there exists such a Y. Okay, then now you look at this collection. All X in Y such that X does not belong to X. This is the intersection of the class defined by the formula X does not belong to X with the set Y. Okay, and therefore Z is a set. And you do the usual argument, ask the question if Z belongs to Z, and you all know the famous argument by Russell that if Z belongs to Z, then Z does not belong to Z, and if Z does not belong to Z, then Z belongs to Z, and you get a contradiction. So Russell's paradox becomes actually a theorem. Okay. So I have also given you example of a proper class. In other words, the universe that you fix will never be a set. Okay. So by the way, let me go back a bit. So here, when I said the universe is not a set, that means it does not belong to itself. Because once you fix V, what do you mean by set? You mean by set the elements of V. Can you admit him, please? He is coming on my yeah. Yeah. So now what I am going to say is that when is a formula psi is true in a class M. Okay. Now, suppose my class is M itself, but this consists of x equal to x. This consists of all sets. So, psi is true in V just means that psi is a theorem. You will see that offset theorem. But if you take a class M and it is defined by phi, then what do I mean by psi is true in M? Then I'm going to define the notion of relativization of psi to the class M. Okay, and since M is defined by the formula phi, the notation for relativization of psi is psi phi. Essential idea is that you think of restrict your universe to M. By sets you mean M only. And then wherever it comes, there exists X. You demand that there exists X, such that X belongs to phi X is also true. In other words, there exists X in M, you should say. And that is how I am going to define it. Now, some amount of logic is needed here, because formulas are defined by what? You start with atomic formula and then go on operating negation or, and build all the formulas. So that is what I am saying, that we define by the induction on the complexity of psi. So what is the definition? If psi is atomic, then relativization of psi to M denoted by psi phi is psi itself. This is the least complex formula of any theory, any language, if psi is an atomic formula. And then note that X belongs, so in case of set theory, there are only two atomic formulas. X belongs to Y or X equal to Y, where X and Y are variables. Now, let us go to more complex formula. Suppose you have defined relativization of eta to phi. Then relativization of negation eta to M or phi will be just negation of eta. Okay? And if you have, this is where the crucial thing is, and if your psi is like there exists a variable V, eta, then the relativization will be there exists V, but this V should be in the class defined by phi, which is called phi V, which is expressed by phi V and eta phi. Okay? And in this case, usual thing, where how does this come very often? Sujata? So, okay, I know what I am doing. I am going down. So, no, it is not helping. If psi is eta or xi, and you have already defined eta phi and eta, psi phi, that means relativization of eta and psi, then you take the disjunction of eta and eta phi and psi phi, that is your eta phi and xi phi, and that is your psi phi. So now I have defined all the, for all formula psi, I have defined psi phi, because you build according to the complexity of the formula psi. And when you say phi x is true in M, by that we really mean that psi phi, psi is true in M. By that we mean that psi phi is provable using axioms of set theory. So again, you see.
Sir, I have a question.
Yeah, please.
What is relativization?
That is what I have defined here. So do you know what is a formula?
Yeah.
So you start with the atomic formula.
Yep.
Then the relativization of atomic formula is itself. Okay?
Yeah.
And suppose you have defined eta phi. That means eta is a formula and you have defined its relativization to M. And now your formula psi is negation eta. Then you call it psi phi, you define to be negation of eta phi. Okay, and so on. If your psi is, there exists V eta, if it is of that form, and you have defined eta phi, then psi phi is, there exists V is in M. So that you express by saying phi V and eta phi, and continue like this. Okay. So you have defined for atomic formulas, then you have defined for negation of atomic formulas and the disjunction of atomic formulas. Again, continue and go on. And in this way, you will be able to define for, you have defined it for all formulas. Is that clear?
Yes.
Okay, good. Okay. Now comes one axiom which is extremely important, and this is an axiom which is not used in mathematics. And therefore, those who are only trained in mathematics don't know this axiom. And this gives us a kind of view, I mean, puts a picture of V in our mind. So it is a very, very important place, important area of axiomatic set theory I'm into. So, okay, so this is not what mathematicians know, this axiom. Now, I said that it is based on two very fundamental principles of set theory. And this is though it is obvious, but people don't pay attention to it, that in the universe of sets, everything is a set. You are not looking, you are not going on a, whatever you are considering, whatever objects you are considering is a set. Well, this has an implication that elements of a set are sets, and elements of a set, elements of a set are sets, and so on. Okay. Now, how do I express this? By which axiom? Because everything is has to be governed by the axioms of set theory. So how do you do that? And here is a big revelation to you. Big. There is an axiom which you know, whose implication you don't know, that what a big implication it has. And so look at this. So this is an example of a formula of set theory. I'm only using usual logical connectives and so on, and the notion belongs to, and building up this. So when I say formula, formally expressible like this, I mean an expression like this. Now let us read this axiom. How do common man read this axiom? Two sets are equal if and only if they contain same elements. Okay, this is something that is immediately first thing you learn. Okay, but read it carefully. Take any two sets X and Y. Then X and Y are equal if and only this Z is also varies over the sets. If and only if X and Y contain same sets. Okay. Now, how does it rule out How does it imply this? Elements of sets are sets. So this axiom has to be satisfied. Now, to the children, and in the beginning, you will accept that suppose I consider X to be collection of all males who are listening to my lectures, and Y to be the collection of all females who are listening to my lectures, this particular lecture. And suppose you assume, you say, oh, this is a set. But X and Y contain same sets, because neither Maya is a set nor Saurabh is a set. Okay? So this part is satisfied, that X contains a set Z if and only if Y contains that set Z. Okay? But you know that they are not equal. These are two completely different, if you accept them to be the sets. And the implication of this axiom is precisely what I am saying. Okay? So only way you have that things are ruled out is that collection of all males in this lecture is not a set. Okay? So you build everything from sets itself. You may ask that, oh Baba, does there exist a set at all? You may have a doubt. Then you may say, okay, look at the formula X not equal to X. Or, oh, by the way, sorry, there is an axiom of set theory, Jdf, which says there exists a set. In other words, formally it is written as there exists X equal to X. So can you help me, Sujata or Arpita, to go to this screen? What do I do?
Yeah,
Can you stop sharing the screen? You want to go to the iPad?
Yes. So, where is it? Stop sharing. So I stop sharing the screen. Okay.
Yeah, and start sharing the other screen.
Yeah. Sorry. So there is an axiom. There is an axiom of Jdf, in fact, the very first axiom, which says there exists a set. Okay? But if any axiom has to be expressible by a formula. So how do you express it? So this is expressed by there exists X equal to X. X equal to X is a logical axiom. So whatever may be X, it will be always satisfied. And since I am looking at only, it is saying there exists a set X which is equal to itself. Every set is equal to itself. So it amounts to saying that there exists a set. Okay, formally. You see how clever we are. Now, how do you show that it is a theorem of Jdf that empty set exists? That means there exists a set which contains no set. Now, by this axiom, set existence, name of this axiom is set existence. Okay? So you say by set existence, let Y be a set. Then, by comprehension, or subset axiom, set of all x in Y, x not equal to Y, x not equal to x is a set. Okay. By extensionality, it is unique. That means empty set is unique. If you have a set which contains nothing, if you take two such sets, they contain same sets, and therefore they are equal. Okay? So here is the first, if you think so, I mean, for you, first concrete example of a set. First, provable example of a set. Empty set, which we denote by phi. Okay? Okay. Sujata, I am. What do I do? I now stop sharing here.
Yeah, please stop sharing here.
Yes.
Start sharing.
Good. Oh, madam, you know what? Okay. Okay. So what I'm saying that the universe of in the universe of sets, elements of sets are sets, and this is not that I'm saying. It follows from the axioms of set theory. Okay. I only took care of one of your discomfort, that how do we know there exists a set? So of course that is put in the axiom. But then no concrete example of sets may be visible, so to speak. I have shown you there exists empty set. And then there are other axioms which will say that from empty set you can build up many sets. Okay. Now the foundation axiom says that there exists no infinite sequence xn of sets such that x1 belongs to x0, x2 belongs to x1, ... so on. Okay? There is no such set. There is no such sequence. And as a consequence, you can prove that there exists no set X which belongs to itself. Because suppose there exists a set X which belongs to itself, then you take the constant sequence X. So that is a theorem of Jdf. And the reason that it is called a foundation axiom is as follows. That now let's come back to your naive set theory. You know binary relations. And when is a binary relation called well-founded? So a strict partial order is called well-founded if there is no infinite descending sequence. Okay. Now here belongs to is a binary relation. Okay. And it just says that there exists no, that the belongs to is a, so to speak, well-founded relation. Now, this is an extremely, this is used left and right in axiomatic set theory. Why? Try to imagine a set X. Then below this, so I'm trying to conjure an example of I'm trying to conjure the picture of a tree in your mind. It's set as a tree. So the root is x, or you say it is going downwards. So x is at the top. Below it, all elements of x. Then take any element of x. Below that, all elements of that, and so on. If you try to view x like this, from x you build this tree, it just says that it does not have an infinite branch. Okay? And such trees are called well-founded trees. Okay? So given a set x, you have a picture. And what it happens is that it tells you that how the x has been built. Okay? Not only that x consists of all its elements, but then you ask that how did you get those elements? They have been built by, again, set up all its elements and keep on doing. All these goes in the building of x. So you may think of x and all the building blocks of it as a tree, and the foundation axiom tells you that this tree does not have an infinite branch. Okay? Now, how mathematically make use of it? You see, this is where I call that you can do induction on tree, on well-founded relation. So if you take a set x, each branch will end up somewhere. Usually in the language of graph theory, they are called leaves. Okay? And then the properties of leaves will imply, so from there you can climb up and go to the next higher level, and the higher level. So in this way, you can use induction. Okay? So the notion of induction, which you are familiar with on natural numbers or on ordinal numbers, if you know more of set theory, is also extendable to induction on well-founded trees. And this is a very, very profound statement in the sense that it is used left and right in axiomatic set theory. And that is how we will use it. And if it so happens that your well-founded relation is also a linear order, then it just says that your linear order has no infinite, strictly decreasing sequence. Okay? And that they are precisely well-ordered sets. Okay? So this foundation axiom or corresponding well-founded tree or well-founded partial order is the generalization of generalization of ordinals, okay, which are generalization of natural numbers, and then you keep on extending the notion of the technique of induction on such objects. So somehow you have to visualize, okay, and we proceed with this. There should be no n, means property of x0 should be reflected by elements which are elements of x0. Then the property of them are reflected by elements of theirs, and so on. And if there is no n, then you know that you can climb up and come up to the x from the leaf.
So can I ask a question?
Yeah. Who is this?
So I'm Ashutosh. I'm a faculty member at IIT Kanpur. So typically when foundation...
Yeah. You are a set theorist.
Yeah. So there's a curious thing happening here. So the way you state foundation axiom that there's no infinite descending sequence under membership. So this is not how generally people state foundation axiom. They state it by saying every non-empty set has an epsilon minimal member. Right?
Well, that will
of course it implies this version, but you need dependent choice. Like
yes. I
agree working in
with
ZF,
you.
right? So
I agree with you. Let me be a bit informal.
Okay, fine.
Sure. Okay. For example, you don't define well-ordered sets by linearly ordered sets, which has no infinite descending sequence.
Every non-empty set has a least member. That's what.
There also you first say that every non-empty set has a least element. Okay. Okay.
But I'm asking a technical question. So do you know if this version of foundation is enough to prove the other version of foundation without assuming choice? So
no, I'm not claiming any such thing. At the moment, I have told you that I am putting a lot of technicalities under carpet.
All right.
I'm only using those which will help me to convey my thing. You see, I am up against a very big task of giving an overview of forcing.
Yeah.
Okay. So I have made such compromises. You will Ashutosh, very nice to hear from you for the first time, and I was very happy to see that there is a set theorist in IIT Kanpur, in India, yet another. And the thing is that at the moment I am here, there will be a lot of such things in my lecture, and that is only to simplify my life and try to convey my thing as quickly as possible. Okay. So with this admission, can I go ahead, Ashutosh?
Sure. Yeah, I was just wondering because it's a technical question and I don't know the answer. If this version of foundation implies the other version,
no.
DF minus the other axioms. Okay, so there's a model where it's false.
No. For example, well-ordered sets itself. If you want to have two versions, descending sequence does not exist a descending sequence, and every non-empty set has a list element, you cannot avoid choice, at least dependent choice.
All right.
Okay. There itself you can see. Okay. You don't have to go to well-founded relations, partial order.
I mean, what is the model where this is witnessed, that this version of foundation doesn't imply the standard?
Here is coming up. Oh, okay. No. Wait. Let us not go into technicality. There will be, as I have told you, that let me work with even a simpler definition. Okay?
Okay.
Because then there is no end to it. I mean, there will be a lot of technical questions that you will ask. You will see that I have even made a wrong statement.
Sure, you should go ahead. I think, yeah.
And I will tell you that I'm cheating. And I have a reason to cheat. Otherwise, life will be a bit difficult for my young age students.
No, sure. Yeah, go ahead.
I have one question.
Who is this Fred?
Yes. What do you mean by an infinite sequence? Do you define infinity or?
Well, everything is being developed inside Jdf. Everything is being developed inside Jdf. So Jdf is your meta theory.
Yeah, it's a function whose domain is omega. All ordinals you can define in without foundation. Everything goes through.
Okay. So there is a meta theory. You cannot develop anything without using a meta theory. The meta theory is Jdf. Okay. That will be my answer.
Okay.
Hi, this is Ananta. I have a question. It's a kind of a naive question in the sense that how do you express this foundation axiom in first order logic? Let's say, so for the first axiom.
Well, let me tell you one thing. The sequence is a function on natural numbers. Okay. And then you write down for all natural number n, xn plus 1 belongs to xn.
Okay.
Okay.
But we don't have natural numbers in the axiom system, right? So first we need to define natural.
Wait. I'm assuming I'm developing whole thing in Jdf. There is a meta theory working.
Okay.
Okay. So I agree that I would have been safer if I had said that, but then I will need this particular thing, then I will prove it, and then again your question will come.
Okay, thanks.
Okay.
Okay, thanks.
But this is expressible in first order language. So there is a Jdf also operating on it. Okay. Now because of the foundation axiom, we are able to define precisely the class of all ordinal numbers. Okay. So now you will see a bit more clearly that why the notion of class is so important. And from here it will be there. Now I call a set X is called transitive if every element of X is an element of X. That means for every Y belonging to X is a subset of X. Okay. And sort of it is saying that the restriction of belongs to X is a transitive relation. That is how it's said. So this is a definition. You may think of, if you want me to give examples of classes, then look at the collection of all transitive sets. Okay. So when it's set X transitive, you now write down the formula phi X, which says that for all Y, for all Z, Y belongs to X, Z belongs to Y, implies Z belongs to X. Okay. So this is a collection of all transitive sets is expressible formally in a first order language of set theory, and therefore it is a class. And then von Neumann defined ordinal number to transitive sets such that epsilon restricted to alpha is a linear order. So only thing that is in any case it is since it is a transitive set, epsilon belonging to alpha is a transitive relation, and now you have to say it is a total relation. Okay, and this can be expressed easily by a first order formula. So I said here the class form. That means what I am describing is a class, is expressible, membership to it is expressible by a formal sentence of first order theory. So this I am leaving as an exercise, but I have also solved it more or less. And this is the notation, very standard notation for class of all ordinal numbers. Okay. Now, again, I'm not doing this, but you can see here foundation axiom will play a role that for each ordinal number alpha and epsilon restricted to alpha is a well-ordered set. For any two ordinal numbers alpha and beta, so now alpha and beta are ordinal numbers. You show either alpha and beta are same, or alpha belongs to beta, or beta belongs to alpha. Very clear, because it is a linear order. Now, here comes, you see this part you can also think of naively. Now comes the most serious statement. This requires a proof that every well-ordered set is order isomorphic to a unique ordinal number. Okay, this requires a proof. Okay, this is where you will be challenged.
I think your second statement also requires a proof. It goes by
No,
saying for any two
no.
well orderings, one is isomorphic to an initial segment of the other, or the other.
Wait.
That's how you show this. I mean, the analog of that argument.
I'm saying that belongs to is a transitive relation.
So for each alpha, the membership restricted to alpha is transitive, but that doesn't imply if alpha and beta are two ordinals, then either one of these must occur, right? You will get this if there is another ordinal that contains alpha.
Okay. In that way, you are right. Okay. And thing is the following: I could have gone to a bigger ordinal, beta followed by alpha, or something like that. But you are quite right. You are quite right. Okay. But in any case, what is called trichotomy is what, in fact, alpha belongs to beta, henceforth it will be expressed by alpha less than beta. Sure, what you are saying is right. Okay. If alpha and beta are ordinal numbers, and if alpha belongs to beta, we write alpha less than beta. If alpha has no last element, then alpha is called a limit ordinal. And if alpha has a last element, say beta, so it is collection of all ordinal numbers less than equal to beta, then we denote alpha by beta plus 1. Okay, and they are called successor ordinals. I will not need more than this. Okay. Now, we call alpha a finite ordinal or a countable ordinal, and I'm excluding the case because finite is here already there, or uncountable ordinal, or ordinal of cardinality kappa. So again, I have not yet defined cardinal numbers. I will soon be defining. If the underlying set is respectively finite or countable or uncountable or of cardinality kappa. Okay. Now, there are a few statements that I am saying. It is not very hard to see that if alpha is an ordinal number and beta belongs to alpha, then beta is an ordinal number. Okay. And alpha is precisely all those beta in ordinal numbers which belongs to alpha, obviously, but that means beta is less than alpha. Then now this statement as a least element. Otherwise, you can keep on producing an infinite descending sequence. Now, these are, I am going to assume essentially that union of a set of ordinal numbers is an ordinal number. So, union of a set of sets is a set is being used here, is an ordinal number. Now I am going into, you can see that whether I can define cardinality or cardinal number of every set, and it requires axiom of choice, at least in the form of, so they are equivalent, well-ordering principle. And this you can prove in set theory very easily. Just the usual proof of Cantor can be translated. So we have that cardinality of X is less than cardinality of power set of X. And I have taken the naive definition, which can be formalized now. That for every ordinal number alpha, there is an ordinal number beta such that mod alpha is less than mod beta. Namely, you take the power set of ordinal number and then well order it. And you will be able to show that the cardinality of beta is bigger than cardinality of alpha. Therefore, given any ordinal number alpha, there exists a least ordinal of cardinality bigger than that of alpha. Okay, there is no end. Why? Because take an alpha, take a beta like this, and now in this, so you consider all the ordinal numbers whose cardinality is bigger than alpha, and it is in beta. That is a non-empty set, and you, or which is okay in beta plus 1, and then that is a non-empty set, and you take the least ordinal of that. Okay.
So maybe it should be mentioned that the fact that for every ordinal alpha, there is a ordinal of a larger cardinality does not need the axiom of choice, because we will be showing later on that ZF plus negation of AC is relatively consistent.
What are you saying? Repeat that again,
For
please.
every alpha, there is a cardinal alpha plus bigger than alpha. It does not need well-ordering principle or the axiom of choice, right? By Hartog's construction.
Okay.
Relevant because we will show ZF plus negation of AC.
Yes, I agree with you. But yes, so it does not require I can get round with it. You are quite right. Okay. In other words, in Jdf also, I can I can prove this particular result. Yes. Granted. Okay. Now here is something I'm doing induction in class on. And well, on is not a set. Okay. However, there are results which says that, if you do induction on, what you get will be a class. That means alpha going to V alpha, the graph of that will be a class. This is a theorem, a big theorem. One can see Cunen's book for this. In the very beginning itself, he has proved it. So now let us begin by, I'm going to give a picture of V. Start with the empty set called V0. Then suppose you have defined V alpha. So I am at the successor state. Define V alpha plus 1 to be the power set of V alpha. And if lambda is a limit ordinal, and if you have defined all the previous V alpha, then take the union, that is the V lambda. Okay. Now here you will see that there is a transfinite induction going on, but it is going on a class. So really speaking, I am defining a function alpha going to V alpha, okay, by transfinite induction on. And there is a theorem which shows that this is a class. Okay, and now well-founded axiom is used here very seriously to say that V is union alpha V alpha. Okay, in other words, for every x there exists alpha, x belongs to V alpha. For every x, yes, there exists an alpha in on, and x belongs to V alpha. You can prove this theorem, and this is precisely why the foundation axiom, as I was saying, is extremely crucial. Now, take any x, it belongs to some alpha, but that alpha cannot be a limit ordinal, because then it has to, so look at the list ordinal, list alpha, so that x belongs to V alpha. that alpha cannot be a limit ordinal. Therefore, it has to be a successor ordinal. So we define rank X to be the first alpha such that X belongs to V alpha plus 1. Okay. This will be help us technically, because I will be able to do two results about sets X or all sets X by induction on the rank of alpha. Okay. Again, here the induction, transfinite induction on ordinal numbers is extended on the class. Because collection of all ranks is precisely on. Okay. Now here comes the definition. A cardinal number is an ordinal number kappa such that for every ordinal number alpha less than kappa, there is no bijection between alpha and kappa. That means cardinality of alpha is less than cardinality of kappa. Okay, these are also called as initial ordinals. So by the well-known principle, for every set X, there exists a unique cardinal number kappa, so that this happens. This also uses that exercise that I have given, that every well-ordered set is order isomorphic to a unique ordinal number alpha. And that particular kappa is called the cardinality of X. Okay, and you have now got your familiar notation. Cardinality of X equal to cardinality of Y. Now this is a well-defined thing, but this is how initially Cantor began operating if there is a bijection between X and Y. Okay, by axiom of infinity. By the way, what is the time? I still have 9 minutes. By axiom of infinity, there is an infinite countable set. Okay, I am not going to explain to you, but usually it says that there exists a set that contains empty set, and if it contains the set X, it contains the set X union singleton X. Okay, again, you have to know the axioms well to show that X union X is a set and blah blah blah. X union singleton X is a set and blah blah blah, whatever. And if you think of it using all the foundation axioms and so on, such a set is a infinite set. So axiom of infinity says that. And then these are also called inductive sets, and sort of the smallest inductive set you can define. This is actually you are increasing, and there is a relation already belongs to relation going on. Oh, so this is what we denote by LF0. Okay, there is a unique list in finite cardinal number which is denoted by LF0. Okay, and now suppose I have defined this. So I am defining what I call, somebody have just now used that term, Hartogs LF. So this is first Hartogs LF, LF0. And then by induction on alpha, I am defining LF alpha for all alpha. So suppose you have already defined LF beta for beta less than alpha, then if alpha is a limit ordinal, we define LF alpha to be the union of all these. And it requires to be seen that this will be a cardinal number. I'm assuming that. And if alpha is a successor ordinal, then you define LF beta plus 1 to be the least cardinal bigger than LF beta. Okay? And what is next? I'm going to now describe, coming close to describing continuum hypothesis. So, if kappa is a cardinal number, it is also a set. So, power set of a kappa, and that has a cardinal number, which we denote by 2 kappa. And all the jhamela and problem arises where in this heart of where will be 2 to the kappa. Cantor was only connected with real numbers and such. I mean, was only considering such. And he had a notion of countably infinite set or omega or set of natural numbers. And then he was trying to show that, the next cardinal is that of real numbers, which he couldn't prove. And we know the reason why he couldn't prove. And this is not very hard to show in the sense that this LF0 is actually the set of all natural numbers. If you do set theory properly, you will see. Then you have a canonical proof of 2 to the set of natural numbers, that means sequences of zeros and ones and R have the same cardinality. Okay. What is the time now? Okay, this is something. Let me see if I can get through. Now, absoluteness is a very, very serious notion. So let me see if I can convey it to you. Let M be a set or a proper class, and XY belongs to M. What should be the definition of X is a subset of Y in M? Okay, in M, because it may be that your model is M. So X is a subset of Y in M is a pertinent question. It says that whenever there is an element Z of M that belongs to X, it belongs to Y. Okay, because I'm saying X is a subset of Y in M. So I'm only considering elements which are in M. See, one way of seeing also, suppose you are looking at polynomials in one variable, and it so happens that all the coefficients are real numbers. Then you ask, what are the zeros of that polynomial in R? What are the zeros of that polynomial in C? Okay, so it is relative to what is your world is, what is your field is. So it is not something very exotic I am talking about. So now assume that with M is a subset of N. Now if XY belongs to M, and if M is a subset or subclass of M, then obviously XY belongs to N, and a phenomenon occurs. Suppose X subset of Y is true in M. Is it true that X is a subset of Y in N also? And look at the difference now. This asserts that if any element of M that belongs to X must belong to Y. This asserts that elements of N that belongs to, so now it is a larger class or set. If it belongs to X, then it belongs to Y. Since it is larger, it is quite possible that X may contain an element Z that does not belong to M, as well as to Y, but it belongs to N. Okay, and now I am going to cheat you to show an example. Okay, so in that case, we cannot say that this implies this. So answer to this may not be always true, may not be always yes. Now this is where I'm giving you an example, and I will tell you why I am cheating. So set theories should shut up. They should not raise any objection. So let M equal to the set consisting of 1, singleton 1, doubleton 0, 1. And N consists of 0, 1, singleton 1, doubleton 0, 1. And take X to be 0, 1. So that guy belongs to M. Take Y to be, take Y to be singleton 1. Then X is a subset of Y in M. Okay? Because only element of Y is 1. Okay? Only element, so only element of Y, no, what do I have to say? Only element of M, which is in X, happens to be 1. And that belongs to Y. So X is a subset of Y in M. But both 0 and 1 are elements of N. Okay? So you can't say that there is an element of N, namely 0, which belongs to X, but does not belong to Y. So I can't say this, that it belongs to N. And why I am cheating is that I am thinking as if one is a set, one is a, I have already told that elements of a set is a set. But I am thinking as if one, which does not look like a set to me. In fact, it is very formally speaking, singleton 0. And 0 is empty set. Okay, so if you try to expand this in that way, then I'm not very sure what I am talking is even right. But it will be very, very easy for me to conjure some example where I will be right. So with this amount of admission that I am cheating, I'm telling you that such a phenomenon can happen. So just think naively, and like you were doing naive set theory, and take M, take N, take X to be this, take Y to be this, define your concept like this, and then you will see that something that you don't expect to be true probably or may surprise you. But if you think a little bit more, that no, there's nothing surprising about it. So this is same thing that I am saying, that a polynomial may have a root, real root, but may not have a real root, but have a complex root. Okay, and yes, I will stop now with this exercise. If M and N are transitive, and if X subset of Y is true in M, if and only if X is a subset of Y is true in M. Okay, this is not very hard to prove, because I had broken that relationship. I mean, transitiveness was not present in my examples. Okay, I think I want to stop here because I will begin with the concept of absoluteness in the next lecture. And I invite questions, quick questions, if you have. particularly from students. And Purvita, don't share the slides at the moment with the audience, because I don't know, in the second lecture, it does not seem that I will change, because so far I have no difficulty, but it may be that after looking at it, subsequent part I may change, but quite likely I will not change. So after my second lecture, you can share it with everyone, so that people have a sort of note also. Okay.
I guess there is no question for today. Okay.
So you give me leave, Chutti?
I guess so, because there is no question right now. So, yeah.
Okay.
Yeah, sure. So we may just conclude the lecture for today. So hope to meet all of you in the next week again. At 7, right? 7 p.m. Yeah.
Yeah. Now at 7 we'll do. And the real thing, I was just giving a, you can say some kind of axiomatic set theory and text of axiomatic set theory I was giving. And if you see the next slides, then our topic begins. Okay. So I'm at least stopping the screen sharing.
Yeah, the share screen. Yeah. Okay.
So Fred, bye. Okay. So can I leave now?
Yeah, sure. I'm just.
Thank you, Sashi.
Yes.
Just thank you.
Oh, how come you are in the office so early?
It's his home actually. Office in his own home.
You have converted a room in your office, in your house to your office.
Yeah.
You are also, jobless like me. Now.
That's right.
He's in LA. He's in